In this video, we're going to develop a general procedure to change from one basis to another. Let's go back and reevaluate eigenvalues and eigenvectors in terms of linear transformations. Suppose that we have this linear transformation T that goes from V back into V. Then a non-zero vector, which is in V, is an eigenvector of T for the eigenvalue of lambda if the linear transformation of that eigenvector is equal to a multiplier lambda times that V. So let's take a look at an example. So suppose we've got this linear transformation of matrices of size 2 by 2 back into matrices of size 2 by 2 given by this. Now remember, linear transformations, okay, you want to think about it as almost like a function, right? It's telling you what to do with the domain and how it's going to look in the codomain. So if you have a matrix which is of the form A, B, C, and D, then what you need to do to it is take negative 17 times A, 11 times B, 8 times C, and negative 11 times D. And that's going to go in that first position in the new vector. And then you can see what's going to happen in the other position. So this represents what you should do to put in the A11 position, the A22 position, or the A12 position, the A21 position, and then this is what you would do to put it into the A22 position. Now suppose we have these vectors, x1, x2, x3, and x4. We would like to find out what the eigenvalues would be. We think that these vectors might be eigenvectors, but we're not certain. So let's see if these truly are eigenvectors or not. So what we do is we put this into the linear transformation. So using this for the first position, wherever I see A, I'm going to put in 0. Wherever I see C, I'm going to put in 0. And wherever I see D and B, I'm going to put in 1. Well, when I put in A 0 and C is 0, I get 0. When I get D and B to both be 1, I have basically 11 minus 11, so that first position is 0. I'm going to repeat the process for this. So wherever I see A, it is again 0. Wherever I see C, it is 0. And then I have 35 minus 33 because B and D are both 1. And I end up with 2. And I complete this all the way through, and I get 2 times that vector I started out with. So putting this vector into this linear transformation, I have the exact same vector out, but with a multiplier of 2. So that tells me that this vector really is an eigenvector, and the eigenvalue attached to it is 2. And I would check all the rest of them, and when I checked all the rest of them, I have these eigenvalues of 2 and 2 and negative 1 and negative 2. So it's kind of cool. Let's take a look at our next example. It's a linear transformation of polynomials of degree 2 into polynomials of degree 2 or less, and it's given by this, where if I have my entry is a plus bx plus cx squared, excuse me, sorry, then what's going to get kicked out into my codomain is 15a plus 8b minus 4c and negative 12a minus 6b plus c 3 times the x, 24a, excuse me, I'm sorry, and then 24a plus 14b minus 7c x squared. So we have these vectors. So my first vector is 1 minus x plus x squared, and my second one is x plus 2x squared and 1 plus 4x squared. And I'm going to do this for each one of them. So just like I did before, I'm going to be putting these into my linear transformation. And when I put in 1, negative 1, and x squared, using the fact that a happens to be 1, b happens to be negative 1, and c happens to be 1, then I have 15 plus 8 minus 4 gives me 3. Negative 12 times 1 minus 6 times 1 plus 3 times 1 ends up giving me 3x. And then in the last one, I get 24 times 1, 14 times 1, and 7 times 1, and that's because my A is 1, my B is, negative 1, and my C is 1, and I end up with a multiplier of my original vector. So 3 of my vector w sub 1. And I do this, and so I end up with lambda 1 is equal to 3, lambda 2 is equal to 0, and lambda sub 3 is equal to -1. Now, here's a little note. Since lambda sub 2 is equal to 0, that means that w sub 2 is a non-trivial element of the kernel of R. Therefore, we know that this linear transformation, because I get a lambda of equal to 0, is not injective, which means it is not isomorphic. Let's take a look at the definition of the change of base matrix. Suppose V is in victory, is a vector space, and we have this identity linear transformation. That's how it's noted as I, and then it's a V. It's an identity linear transformation from V back into V. Let B with the vectors V1 to Vn and C also have vectors, be two separate bases of V. Then the change of basis matrix from B to C is the matrix representation of this identity linear transformation relative to B and C. This is how we note it. So the change of basis matrix from B and relative from B to C is the matrix, noted M for matrix. The IV is the identity linear transformation from B to C, which is the row of C. Now, if you remember from our previous videos, row of C is the vector representation of the the identity linear transformation of V1. So each one of these here just means that it is the columns can be filled in with the vector representation of C with respect to the identity linear transformation with each one of the V1 all the way up to Vn. Then that gives us this theorem that says, suppose V is a vector space, and V is a vector in the vector space big V, and B and C are bases of V, then the vector representation of C with V is the change of basis matrix, where I have B onto C, which is the vector representation of B with respect to V. Whew, that's a lot. This theorem basically means that the change of basis matrix can be used with matrix multiplication to convert a vector representation of V relative to one basis to a representation of a vector relative to a second basis. So here's our theorem, another theorem we've got, which is the inverse of the change of basis matrix. Suppose V is a vector space with B and C are bases, then the change of basis from B to C is non-singular, and that means we can invert it. So if we invert it, we invert that matrix from B to C is going to be, when it's inverted, is from C to B. So let me give you some notations and hopefully kind of standardize some of what's going on here, make it easier to think about. Now, if we consider the vector V, and I'm going to subscript this with S. So this is the standard basis. So standard basis, as an example, would be, the standard basis would be if we're in R2. So in R2, the standard basis would be the vectors 1, 0, and 0, 1. And we talked about this, how we prefer those, but life isn't always about the standard basis. And so this is the subscript for the standard basis, and I list as an example in R2. Now, if we have a linear transformation that's going on, and we've got B, which has all these vectors. B is my basis, and it has the vectors, we'll call them B1, B2, B3, etc., all the way up to Bn, which can be represented as the matrix U, where the columns are B1, B2, B3, all the way up to Bn. Then if I take my U matrix and I multiply it by my vector v, which is in respect to my basis b, it's going to give me my vector v with respect to the standard basis. Now we know that since U is built of linearly independent vectors, and we can assume that it is non-singular, then v, my vector v, with respect to b is going to be U inverted multiplied by my v, vector v, with respect to my standard basis. Cool. Now, if I have C, I'll do this C. If I say C is another basis, which has the vectors, and these are all vectors, by the way. These are vectors. It has C1, C2, C3, all the way up to Cn. Then it can build, and I'll call it, oh, what do I want to call it? Don't want to use V. Let's use W. Can be the matrix W, where each one of the columns are going to be these vectors, but now as columns, all the way down to Cn. Just like before over here, where we said that my matrix U multiplied by some vector V with respect to the basis B will give me my vector V with respect to the standard basis. The same thing is going to be true over here. So W, the matrix W, multiplied by this vector V with respect to the basis C will give me the vector V with respect to the standard basis. Similarly, the vector with respect to the basis C is going to be equal to the inverse of W multiplied by my vector S with respect to the standard basis. Now, what if I want to go from one to the other? How can I go from one to the other without doing some intermediate steps? Well, these two things are going to help me do this. So I'm going to bring in this idea and this idea so that I can go, if I want to go from one basis to another one. So suppose I want to go from my vector with respect to C, and I want to go from there to my vector V with respect to B. Well, the way I'm going to do that is I'm going to bring into these two things I've kind of highlighted in green, which is this information and this information. Now, I want to end up in V sub B. So V, the vector V with respect to B, is equal to, well, this is U inverse my vector S with respect to S. I'm getting that from right here. However, my vector V with respect to the basis, my standard basis, can be rewrote with W with respect to my basis multiplied by my vector C with respect to my C basis. So then it's just a matter of inverting one, multiplying by another, and then multiplying by the vector that is in respect to that basis that I have so I can get to what I want. So that means that if, suppose I want to go from my vector with respect to B to my vector with respect to C, using the same kind of logic, then my vector V with respect to C must be equivalent to, well, that's going to be W inverse multiplied by my U matrix multiplied by that vector that's given to me with respect to B. So we don't have to go through all those shenanigans to do my linear combinations and writing it in terms of the vector representation. So that's kind of cool if I'm staying within one basis to another basis in the linear transformation. So that's kind of cool. Okay, so say I have these bases and I want to find a change of basis matrix between these two. One of the ways I can do that is I can do the vector representation, just like this. Boom, there it is. There's my vector representation. Now, could I have done this easier? Well, absolutely. The way I'd do that, without doing all of these vector representations, is I would have used this one right here. I want to go from B into C, so I'm going to use that. Go B relative to C. So I would first build my matrix, which is my W matrix, and my W matrix would be 1, 0, 0, 0. That comes from this one. 1, 1, 0, 0. That comes from this element. 1, 1, 1, and 0. That comes from this element. 1, 1, 1, and 0. Oh, I need one more 1. And that comes from that element. So 1, 2, 3, 4. And then, oh, I need, my apologies. I need one more here. And then I have 1, 1, 1, 1, and 1. That comes from this element. Now, I want to end up in my vectors with respect to C. And I have my vectors with respect to B to begin with. So I'm going to have to find the inverse of this. And I'm going to go out and use a matrix inverter. I'm not going to do this by hand. And when I used a matrix calculator, my inverse is going to be, here we go. It's going to be 1 and then zeros beneath it. Negative 1, 1, and then zeros beneath that. 0, negative 1, 1, and zeros beneath that. 0, 0, negative 1, 1, and zeros. 0, 0, and then I have another 0, then negative 1, and then 1. I think I have gotten 1, 2, 3, 4, 5. Yep, there it is. Now, my U matrix is the identity matrix. So that's kind of nice. It is 1, 0, 0, 0. And I need 1, 2, 3, 4, 5. 0, 1, 0, 0, 0. 0, 1, 0. 1, 0, 0. 0, 0, 0, 1, 0. And 0, 0, 0, 1. So when I do W inverse multiplied by U, I'm just going to get W inverse because U happens to be the identity matrix. So when I do W inverse multiplied by U multiplied by the vector, now the vector I have is my B vector. So I'm going to start with a B sub 1, which is this first column, B sub 1, B sub 1. So when I do this, my W inverted multiplied by my U, which is the identity matrix, multiplied by my first vector, when I do this multiplication, I'm going to get exactly the same thing as I did before when I did my linear combinations. And then I have W inverse U, which is the identity matrix, B sub 2, which is this column, gives me the exact same thing as I got there. Excuse me, this one here. And so I can do my matrix. I can find this matrix right here. This, my apologies, my iPad's messing up on me, is going to be done by doing this instead of linear combinations. Linear combinations is not wrong. You can totally do it that way, but we could also do it by using matrices, which is kind of nice. Okay, so let's take a look at this. Now let's consider this vector u, and it becomes with respect to the basis b. So here's my vector under the basis b. This is what it looks like, because remember my basis b is the standard basis, which is kind of nice. We can also obtain the second representation of u with respect to c by using my previous theorem, which says, look at that matrix representation I've got multiplied by my vector with respect to b is just this, which is kind of nice. Let's take a look at another one in which I don't have the identity matrix. Again, totally do this by linear combinations. What I'm going to do though is here's the notes, go through the notes, linear combinations, cool. Let's do it by matrices. So my W, because that's what I used, right? So I gotta make sure my notations are the same. W, yep. So my W matrix is going to be 1, -6, -4, -1, -4, 8, -5, 8, -15, 13, -2, 9, 3, -7, 3, and -6. And I have the U matrix, which is my matrix built from the B, which is 1, -2, 1, -2, -1, 3, 1, 1, 2, -3, 3, -4, -1, 3, 3, and 0. Remember, I want to find a change of basis matrix to go from B to C. So this is going to be my vector V with respect to C is going to be W inverted multiplied by a U multiplied by my vector that I'm looking at with respect to B. So I'm going to go out, I'm going to invert W first. And with my calculator, I get this to be -5, 3, -4, and -8, 5, -6, 7, and 13, -7, 3, -4, -9, -3, -4, 3, and 5. Now, if I multiply my W inverse times my U matrix, which again, this is my U matrix, so I'm multiplying this and my U in matrix, this is going to give me my change of basis matrix from B to C. And I get, and you should check this on your calculator, the exact same thing as if I would have done it by doing linear combinations, finding the alpha 1, 2, 3, because that's what this is all about. As I found the linear combinations, this 1, -2, 1, and -1 is by doing the linear combination. So just as a reminder, another way I could have done this is I would have set it up as alpha 1 times my first B1 vector plus alpha 2 times my B2 vector plus alpha 3 times my B3 vector plus alpha 4 times my B4 vector. And I said it was equal to my C1 vector. So these are all vectors. And if I would have done that and solved that system of equations, I would have got the the vector representation, which is all of my alphas. So I did it that way. Or the change of basis matrix, depends on if I want to go from B to C or C to B. Here I wanted to go from B to C, so it is going to be the inverse of W matrix multiplied by my U, and I am done, which is kind of nice. Now I want to figure out what an arbitrary, let's just choose an arbitrary vector in R4, and what would it look like with respect to B? So again, what I would do is I can do this by doing my linear combinations. So this is alpha 1, alpha 2, alpha 3, alpha 4 multiplied by my B1, B2, B3, B4. I set it equal to this, and when I did it, set it equal to this, I got these alphas. So my alpha times each one of those, or I can use my change of basis matrix, because I'm going from B, that's on my basis B, into C, which gives me the change of basis matrix multiplied by my matrix here, which gives it into my C matrix, which is awesome. We love it. So again, we can do the matrix representation, which makes our life a little bit easier. So let Q, oh, here's another theorem. The matrix representation of change of basis. Suppose that T goes from U into V as a linear transformation. B and C are basis for U, D and E are basis for V. Then I can do my transformation T from B to D is equal to the linear, or the vector matrix change of basis. Man, that was hard to spit out. From E to D multiplied by my matrix that is represented by the linear transformation from C to E multiplied by my matrix from the matrix change of base matrix from B to C. Whole bunch of stuff going on there. So let's look at this example. We're looking at symmetric 2 by 2 matrices, be a linear transformation. This is how we're going to define it. Here's my basis 1. Here's my basis 2 in symmetric 2 by 2 matrices. And I want to find a basis for P3, or they're giving me basis for P3, which is this basis and this basis. I want to find the matrix representation of Q relative to B and D. Now this one's going to be slightly different because of the fact that I'm going from symmetric matrices to polynomials of degree 3. Because this is different, what I'm going to do, because I want to go from B to D, is first I'm going to find a relationship to C to E. Because if we look at what C is a standard basis for symmetric 2 by 2 matrices, and E is a standard basis for polynomials of degree 3 or less. So I want to figure out how I go from a standard basis of 2 by 2 matrices that are symmetric to a standard basis of polynomials of degree 3 or less. So what I do is I set up the equation. So I put in the standard basis into my linear transformation, that's here, and I end up with this polynomial. Now, this polynomial, with respect to E, because E is a standard basis, its a vector representation is strictly just going to be this. So no real thinking process there. I put in this standard basis, so my second matrix that's symmetric, and I put it into this linear transformation up here. That's how it's defined. And I get this polynomial of degree 3. Again, because the vector representation of this polynomial degree 3 with respect to the standard basis is exactly just this. And then I do this for my last one. So then my matrix, which is respect to my linear transformation Q going from C to E is just these vector representations. Now I'm going to construct a basis from B into C. And this I can do like I always do by linear transformations and, not linear transformations, but linear combinations. This 5, this -3, and this 2 come from the linear combinations of what C would look like to get this out, and I get this vector out as a vector representation. The 5, the -2, and the 3. These are all coming from doing our alpha sub 1 times the 1, 0, 0, 0. The alpha sub 2 times the 0, 1, 0, or 0, 1, 1, 0. And my alpha sub 3 multiplied by the 0, 0, 0, 1, and setting it equal to my first B, B1, which is the 5, the -3, and the -2, which is equal to the 5, the -3, and it's 5, -3, -3, 2. And I would do my regular solving, and when I solved, I ended up with this as my vector representation of alpha 1, 2, and 3. And I did it for all three of them. Now, this is the change of base between B, changing from B into C. So I'm changing from B into C. I'm going to do the same thing from my D into E. Now this one I did it by linear combinations, but because of it being nice polynomials, I would probably do it like we did before and do it with a matrix inverting rather than by the linear combinations, but here's the linear combinations. Now, we know the matrix representation, the change of base from E into D, is the same as the inverse of the matrix or the change of base matrix from D into E. So here's my E into D. I invert it and I get this. Now, what I really want to go is I really want to go from B into D. And the way I'm going to do that is I went from E into D, that's this matrix. And then I have the matrix representation of over the linear, it's not linear combination, the linear transformation of C into E, that's this matrix, and the matrix from B to C, which is this matrix. I do all this matrix multiplication, and here is my final answer. Whew, wow, that's a lot. A lot of steps, a lot of things to do. All right. Now, here's similarity and change of base. Now, suppose a linear transformation T is from V back into itself is a linear transformation from B to C. These B and C are bases of V. Then, the matrix representation of the linear combination of B into B is the inverse of the change of base matrix from B to C multiplied by the matrix representation of the linear transformation from C into C multiplied by the change of base matrix from B into C. Whew, holy smokes. Now, let's consider this linear transformation, where these are my vectors, which are, as you can see, that they are really 2 by 2 matrices, but we're going to call them vectors because we're in a vector space. And we know from our previous example that if these were my vectors, we found that these were actually eigenvectors with these eigenvalues that are associated to them. We want to find the matrix representation of the change of base. Since we know the eigenvalues, and you're thinking, why did I need to know eigenvalues? Well, here they come into place. We know the eigenvalues, so if we have the linear transformation T onto X with respect to B, is basically the linear or the vector representation of B with respect to that x sub 1, which is lambda 1 times that x sub 1, which is just this. And then we have the lambda sub 2 times our x sub 2, which is just this. Lambda sub 3 times our x sub 3, which is just this. And my lambda sub 4 times my vector x4 times my lambda 4, which is just going to give me this. Cool. That's kind of cool. So then my linear transformation of B onto B is, notice, are you ready for this? Dun, dun, dun. All of my lambdas along the diagonal. And this should look familiar to you. This is like, oh, I remember this in our previous sections. Now I'm going to do the same thing with our matrix representation relative to C to the standard basis. And the standard basis for a 2 by 2 matrix looks like this. And if I go to my standard basis, choose blue. So I'm going to find the vector representation with my y sub 1, which is 17, negative 57, negative 14, and negative 41. And again, I did linear combinations. That's where I came up with these numbers. And my second one. And my third one. And my fourth one. I get these. Look at that. Again, these I could totally do by matrices like I did before, but this is the nice linear combination. So then here is my matrix with a linear transformation from C into C is this, which is, you know, these are the vector representations. And again, I could have totally have done this by putting these into matrices instead of doing the linear combinations. Now, my vector representation of C with respect to x1 is this, again, with linear combinations. I could totally do this with matrices like I did before, and I end up with this. So these are my vector representations, and they get put into a matrix. Again, C from B into C. Again, I would probably do this by matrices. And we end up with this, which is equivalent to this, which is this matrix inverted, which is this. And so my matrix representation of the linear transformation from B into B can be wrote as the inverse of the change of basis from B to C, multiplied by my matrix of the linear transformation from C into C, multiplied by my C of the linear, okay, where are we now? We are the transformation, linear transfer, or change of base matrix from B into C. And notice how my lambdas, which is part of my diagonalization, can be wrote in this way. So I could find, this is another way to find my lambdas, which is kind of nice. Kind of nice connection. And so what we get is, suppose T is a linear transformation from V into V is a linear transformation, and B is a basis of V, and this vector is in V is an eigenvector assigned to an eigenvalue of lambda. This is true if and only if the eigenvector with respect to the basis B is an eigenvector of my matrix representation of the linear transformation of B onto B for that eigenvalue lambda. This tells us that eigenvalues of a linear transformations are the eigenvalues of any representation, no matter what your choice of the basis B may be. Let's say that again. Eigenvalues, eigenvectors, and characteristic polynomials are intrinsic properties of linear transformation and are independent of the choice of the basis used to construct that matrix representation. So that's kind of cool. Now, let's look at our linear transformation of matrices of size 2. This is how we're going to define it. We want to find the eigenvalues and the eigenvectors of S. Let's start with the easiest standard basis, which is this. We're going to build the matrix representation of S relative to B. So I'm doing my vector representation of B of S with respect to my first X sub 1, which is this, which gives me this. Going through the whole process, I end up with this matrix representation of my linear transformation of S of B onto B, just like we did before. I find the determinant of this matrix, and M, so that matrix minus the lambda and the identity matrix size 4, and I end up with this characteristic polynomial, which gives me these lambdas. And I can then from there do my usual. Here's my lambda, my lambda 3. And I put it in and I row reduce and I find my null space, and here's my first vector that is associated with this lambda. I do the same thing here just like I did when I was finding eigenvectors, and I continue until boom, 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 I end up with these 4 vectors, 1, 2, 3, and 4. And so we know this as a vector becomes this as a 2 by 2 matrix. This as a vector becomes this as a 2 by 2 matrix. This as a vector, it becomes this. And I have found my eigenvectors associated to those eigenvalues. And so, bam, here we are. Here is my eigenvalue, my eigenvector with S with a lambda of 3 gives me this vector, which is a 2 by 2 matrix. My eigenvector with respect to S with a lambda of 2 is this vector, which is a 2 by 2 matrix. And because this has a multiplicity of 2, I should expect 2, and I did find 2. So here is my eigenvectors with respect to S associated to those eigenvalues. Here is my matrix representation of the linear transformation S of C onto C, which is here. And if we use the basis D, you're going to get the same eigenvectors and the same eigenvalues. And boom, that's it for the change of basis.